Okay, it's 3.3. Hoping our contraption holds up. Characteristics of polynomial functions in factored form. So we're going to determine, our goal is to determine the equation of a polynomial function that describes a particular graph or situation, or vice versa. So basically we're going from an equation of a graph to a graph, and vice versa. And the graphs and the equations now are cubic or cortex. Okay, so prior to this, if you saw a cubic function in vertex form, you'd have a good idea of what the graph looked like. Now we're going to show vertex form, or a variation of vertex form, for cubic and quartic functions, and we should get an idea of what the graph looks like. Okay, so the first step, it says solve equations f at x equals 0 and g at x equals 0 using the given functions. So here's our function. What should that give us if we plug in f at x equals 0? What do you guys know about that? Sorry? Well, g at x, okay, yeah, it's negative. If we plug if we plug in g at x is 0, 2x minus 12, we get x is equal to 6, right? Okay. But why do we typically do that? We set a function equal to 0. What are we looking for? Yeah, the zeros. We're looking at where does the graph cross the x-axis. Okay? And we know that because we're setting the y value equal to 0. Okay, so that's going to give us the point at 0. So this g at x is represented by the red line here. I solved for x and I got x equals 6. Okay, so that makes sense. The red line goes through. Now, for the blue graph, I need to factor this. So I do multiply to negative 12, but add to negative 4. So I get negative 6 and 2. So then I get x equals negative 2 and x equals 6. Okay, and that corresponds again to my zeros here, negative 2 and 6. Any questions about that so far? Okay, it says compare the solutions with the graphs of the function. What do we notice? Well, we notice that setting f at x equals 0 gives us the zeros, roots, solutions, x-intercepts. These are all synonyms of each other, right? So they all mean the same thing. The zeros, the roots, the solutions, the x-intercepts. What they're referring to are these points. Okay? And we know that because we're setting the y value equal to 0, and then we're solving where's the point. Okay, so that's pretty much review from grade 10. Next it says create a cubic function from the family of polynomial functions of the form this. So basically it's telling us now to come up with our own cubic function. So we're just going to come up with a function down here at the bottom. So I'm going to write b here. And I'm going to say f at x equals okay, and I just took the random numbers 2 and 1, 2, 3, and I subbed them in for these different variables a, p, q, and r. Okay, so I created my own cubic function here. Next it says graph this function that I created. Okay, so if we had a graphing calculator or your phone app, which I've been encouraging you to get for quite some time now, you'd get a graph that looked like this. Okay, so that's the graph. Describe the shape of the graph near each zero. So each zero is here, here, and here. Okay, those are our zeros. And the shape of the graph is that, well, the graph passes through each zero. Okay, there's nothing really strange happening. There's no turning point happening on the zero. There's no asymptote. to describe it, I would say the graph passes through each 0. Any questions about that? Okay, and compare the shape to the order of each factor in the equation of the function. What's the order mean? Anybody? Order? It's similar to degree, except for it's just any exponent. It's the exponent, okay? So the order in all of these is 1. Okay, your order is your exponent of the 0, so to speak. Okay? The exponent to which each factor is an algebraic expression is raised. So it's right here. So there is my definition, and there's the book, okay? So the order of x to the minus 3 is 2, and the order of x minus 1 is 1 here. Okay? So that's the order. You need to know that. So it passes through the 0, and the order is 1. So we have a relationship when order is equal to 1, the graph passes through. Passes through the 0. Okay? Next it says solve h at x equals 0 and compare your solutions with the zeros of the graph of the corresponding function. What do you notice? So if we set f at x equals 0 now up here, I'm going to have this 0 is equal to this whole value. Doesn't matter what this constant is, right? Because I'm going to divide both sides by 2 and that'll cancel. 0 divided by 2 is still 0. So I have these 3 terms now equal 0. And I explained this extensively in grade 10, why x minus 1 equals 0, and x minus 2 equals 0, and x minus 3 equals 0. There's 3 cases, okay? The reason why is because anything times 0 is 0. So if this value, this multiple is 0, then this whole expression is still true. Okay, so there's 3 separate cases here. There's x minus 1 equals 0, x minus 2 equals 0, and x minus 3 equals 0. Those are our 3 cases to solve. Okay, so x is equal to 1, x is equal to 2, and x is equal to 3. And if I would have had units on this graph, they would have been like this. Okay, so what do we notice? Well, we notice when I set the y value equal to 0 and I solve the equation, that corresponds to the zeros on my graph. Any questions? E, it says repeats b through d using a quartic function. So now a quartic is to the exponent of 4. Let's do that up here. Okay, so here's my quartic function. How do I know it's a quartic function?
What is it for now?
Sorry?
What is
Because it's asked us now to do quartic.
Oh.
Okay?
Oh, okay.
Quartic means x to the exponent of 4. So this is quartic. X to the exponent of 3 is a cubic. X to the exponent of 5 is a quintix. Okay? So it gives us a quartic function. How do I know this is a quartic function? Because if I multiplied all the x's, that's going to give my highest exponent of x, right? So I'd have 2x times x is 2x squared. 2x squared times x is 2x cubed. Times x again is 2x to the 4. Okay, that's how I know this is a quartic function. And then it wants me to solve if I set this all equal to 0. Okay, so I would get x equals 1, x equals 2, x equals 3, and x equals -1. And then if I were to graph this on a graphing calculator, okay, and there's a couple of things we should know already about this graph without using a graphing calculator. Because we know it's x to the exponent of 4, we know that two end behaviors. We know that the leading coefficient is positive, so we know the end behaviors end up going both in the positive y direction. Okay? So we know that because it's x to the exponent of 4. Next, we know all the zeros are. There's one at -1, so this is -1. There's one at 1. There's one at 2. And there's one at 3. Okay, we know that from this equation. Any questions?
So what would be the order for this?
The order would be 1, 1, 1, and 1. Each one of these has their own order, which is the exponent. Yep.
How would you know when you're drawing the little sketch which part of it goes down?
I'm going to show that in a minute. You'll see in the question. I don't know that yet. To answer your question, we just get this graph from the graphing calculator. So far, okay, Luke? Yeah.
Hello, Mr. Bell.
Hi there.
Hi, is Kevin Tolentino in class?
Yes.
Can you come to the main office quickly, please?
Sure.
Thanks.
Okay. So we're beginning to see what we're getting at here. There's a relationship between the equation and what's happening on the graph, particularly with the order and the zeros. Now let's see if we change the order from 1, okay? So we're looking at f now. It says repeat c and d for this function, okay? And we notice that the order is 2 here. What do you think is going to happen, guys? Any guesses? We know something's going to happen at x equals 2 and something's going to happen at x equals -3. Yeah.
The equation will be cubic. No.
You're right. The equation is cubic, so x squared. So you know the n. We know what's going to happen with the n values, right? The n behaviors. Because it's positive a and it's cubic, we know it's going to be like this. You're right. But what particularly about the order do you think is going to happen? Anybody guess? We know something's going to happen at x equals 2 and x equals 3. Something's going to happen here. Sorry, x equals -3. And here. All right, well, let's see. Let's graph it.
So isn't this quadratic? Or?
No, it's quadratics if it's 2, right? Here we go. So Luigi, you may be required. All right. So we're looking at this function now. M at x is equal to x minus 2 squared x plus 3. How would you describe the shape of the graph near the 0 with the repeated factor? So this graph looks like this. And again, to answer Luke's question, how do I know it looks like this? Well, I don't know exactly that it looks like this unless I use a graphing calculator, but there's a few things I do know, right? Because this is x squared times x, we know it's a cubic function. And we know because the a value is positive, we know that the end behaviors are going to look like this. Okay? And then we know at x equals positive 2 here and -3 here, the graph is going to be at 0. Okay? Yeah.
So the other thing we really don't know is where the top of the...
Yeah, we don't know this.
Yeah.
Okay? We also could find this point here. How could we find this point? Sorry?
Expanding?
No, we don't need to expand it. We could and then do something, but that'd be messy, yeah?
X equals 0?
Right, we just set x equal to 0, so we would get -2 squared times 3, so we would get 12. So
It's down in the Not in the.
This would be 12.
So it's not in the shot.
Okay? You just set x equal to 0 and you solve for y. That would give us this point. Okay, so what do we notice that's happening when the order of the 0 is 2? What happens? I'm going to write this down. You guys think about it. When order is 2, so order, and I mean the exponent, is 2. And I'm calling it of the factor because this is a factor of the function. Okay, I'm going to put in brackets there the 0. Okay, because by setting the factor equal to 0, we find the 0. So when the order is 2 of the factor, what happens on the graph? On the graph, what occurs? Yeah. Nope. Come on, guys. Nobody? Really? Joseph. Yeah, right here. Here, I'll help you. Here's what we're talking about, right? Can you see my pen? Okay. So when x equals 2, which is here, what's happening on the graph? Yeah, but what's happening here? Come on. Yeah, it's a turning point, right?
Oh my goodness.
I don't know why that was so hard. So previously, we talked about when the order was 1, we go through the point. So when the order is 1, this is at x equals -3. We go through the point. When x is, or when the order is 2, we turn at the point. Okay? Which makes sense from our, our famous graph of y equals x squared. Guess what? At that point, we turn, right? We turn at that point of x equals 0, y equals 0. Okay? So when we have a factor that's squared, a turning point occurs on the graph. All right, next. We're going to figure out what happens when we have a cubic. Okay, who can guess this graph? This will be pretty good if we can guess it. Elijah, tell me what's happening at the end points. Yeah, what's happening over here and what's happening over here?
So from x going towards negative infinity, it goes downwards.
Okay, let's think about it first. Hold on. What is the degree of this function?
3 would be x by the power of 6.
No. Think about it, Elijah. Yeah. Yeah, it's 4, right? Because it's x cubed times x to the 4. Okay? So the degree is 4. Okay? Gennaro, what's the coefficient here? Positive or negative? What does that mean? When the degree is 4 and the coefficient is positive.
Then variables are the same.
Yeah, and what are they?
Both positive.
And they're both going...
Both approach positive infinity.
Good. Okay. So I've got that far. Next, what are my zeros now? Joseph over here.
-3 and +2.
Excellent. Okay. Alan, at -3 over here, what's happening? No.
0.
Sorry?
It's going straight through.
Yeah, it's going straight through. Okay. Now this is the one we don't know when the degree is 3. Anybody can guess what's happening? So we know when it's x squared, when the order is 2, it turns. If it's not 2, it's 3. Who can guess? Yeah.
It's gonna do like what the cubic function does at x
Yes. And what does it do?
It's gonna.
Yes.
But yeah, it's gonna go
Hard to describe, but basically it kind of evens out and then goes up. And he remembers, the reason he's saying that because he remembers what y equals x cubed looks like, which is like this. Is that right, Alex?
Yes. Yeah.
Yeah. So exactly. So when the order is 3 now, okay, so here's your communication mark here, guys, right? As he said, it's very hard to kind of explain. There's my explanation, the best I could do, right? On the graph, an evening out occurs as the graph passes through the point, okay? This is that evening out. Any questions there? Yeah.
So the x plus 3 is straight, it's not curved.
Yeah, no, it's -3, so it's over here, right? Yeah.
So straight, okay.
Yeah. So there's something else. This turns somewhere up there, like that. Yeah, we could find this point, yeah, by subbing in x equals 0. So there you go. Okay, so we're beginning to figure out a lot of like little shortcuts to graph. Yeah.
So we basically just figure out if it's cubic, quadratic, and then find the zeros and basically try to mimic the graph.
Yes. That's all we've done so far. How about this one, guys? Let me do this.
Yeah.
Oh my goodness. No,
Okay, it looks super duper crazy, but one nice thing is that it's already in factored form. If I would have written this in standard form, you guys really would have had, you know, had something to say. But this is 1, 2, 3, 4, 5. So squared, cubic, quartic, quintic. That's 6, and then plus 4, so we're at 10, right? That's x to the exponent of 10. My coefficient is positive, so I know then my graph on the ends, this is even, and it's positive. So I know on the graphs, the end values are happening like this. Is it 9? 2, 3, 4, 5. Yeah, 9, sorry.
wait, how is it done?
So this is squared. So 2, 3, 4, 5 plus 4 is 9. Okay? So there's my end behaviors. Then I know at the opposite values of each one of these, I have zeros, right? Go ahead. Yeah. Yep.
-3, +7, +5.
Hold on. Yep.
-8.
Yep. Okay, so all of these points I'm crossing through. So the first one, I know I'm going this way. let's say for simplicity reasons, there's no other maximum and minimums, and we're going to talk about that in a second. But let's just say for simplicity. Now there's something happening here at x equals positive 2 to the exponent of 4.
What is it? That's a turning.
So there's a turning point there. I'm going to just... I want to show it a little more. I'm going to put the 4 over here. Okay? Hasn't changed anything, right, in the graph. I'm just putting it over at the 7 so I can show it a little better. So 1, 2, 3, 4, 5, 6, 7. So at this point here, there's a turning point. I need to be coming from this direction in order to end up. Okay? And the other thing I want you to note is the turning point was drawn out. So just like y equals x to the 4 looks like this. That turning point there is flattened out. So the larger the odd or even number becomes, the more flattening out occurs. Okay? So if you have an order, let's say an order of 9, so y equals x to the 9, just for simplicity, this flattening out is going to be huge. Okay? So the order, depending on whether it's even or odd, determines whether it's a turning point or a flattening out. And the number of the order, depending on how high, determines how much it flattens out. Okay? So whereas x to the squared looks like this, x to the exponent of 4 looks like this. X to the cubed looks like this. There's a little bit of flattening out occurring here. X to the exponent of 9 looks like this. A lot of flattening out. Is that clear? You guys understand what's happening now? Yeah. I'll repeat it one more time. So, depending on whether the order, remember the order is the exponent, okay? Depending on whether the exponent is even or odd, determines whether there's a turning point if it's even, or whether there's just a flattening out in the same direction if it's odd. Okay? That number determines how much flattening out occurs on both even and odd functions. Okay? If the number is really high, there's a much bigger flattening out occurring. Okay? You guys get that?
Yes.
That's pretty much it. That's the lesson. Now we're just going to go through some examples. If I can fix my lamp.
Does anyone have an elastic?
I forgot my hair.
Hold it, Andrew.